When working in physics, we have two quantities which we usually use, which are scalars and vectors. There is a huge difference between a scalar and a vector. For instance, a scalar only has a magnitude, while a vector has a magnitude, but it also has a direction. Some people actually also use direction as direction and sense. They break it up, but we are going to only use magnitude and direction. There are certain examples that we can actually state about the scalars. For instance, the distance is a scalar, while its vector is called the displacement. It's a change between 2 points. Time is also a scalar. Speed is a scalar, while velocity is a vector. Mass is a scalar, while the vector is, for instance, a force. It could be the gravitational force, it could be weight, which is kind of the same. And we're going to be working with this kind of quantities during the course. When we're working with vectors, we have to understand that we're representing some phenomena, and we're extracting information, and we have to input that information into a plane. So the Cartesian plane, for instance, when we're working with 3 dimensions, has a component x. It also has a component y, and, well, it has a component z. Now, the z is something that is popping out from the whiteboard in this case. We have to use 2 dimensions in order to represent 3 dimensions, and then we can actually state we have, for instance, any given arrow, which is a vector, and that vector, it has a magnitude. The magnitude has, for instance, we denote it with an absolute number, and this is vector, for instance, A. This vector has 3 components: component x, component y, and component z. Using Pythagoras, we can actually state that the magnitude is going to be equal to the square root of ax squared, its component y to the square, and, for instance, component z to the square. That's the magnitude. And, of course, this guy has direction angles, and each direction angle, for instance, there is a direction angle with respect to x, a direction angle with respect to y, and a direction angle with respect to z. And we usually use the Greek letter theta. Okay, so this is z, this is x, and this one is. So I am working. Sorry. So this is y, right? This is z. And of course this guy, it does not exist. So a direction angle, for instance, if we use trigonometrics, the cosine of the angle, right, for instance angle x, is going to be the adjacent component, which for instance is component x, over the hypotenuse, that is the magnitude of the vector. The cosine y is going to be equal to the component y, right, over the magnitude, and cosine z is going to be equal to the component z over the magnitude, which is the hypotenuse, using trigonometrics. The cosine of the angle is what they are called the direction cosines, right? Direction cosines. There are 3 direction cosines because there are 3 angles, while each angle, for instance, of course, if instead of wanting the cosine of the angle, we want the angle per se, we have, for instance, to obtain the inverse cosine of the right part of the equation. For instance, theta x is going to be the inverse cosine of component over magnitude, and so on and so forth for the rest of them. So each and every direction angle is going to be the inverse cosine of the component over its magnitude of the vector. Now, when working formally with vectors, we usually use a notation that it's the unit vector notation. And a unit vector is a vector which magnitude is 1, and they are usually used in order to denote a direction of the vector. This is very important because usually we are not going to be working with components ax, xy, xz, whatever. We are going to be working with this notation, and these guys are the ones who denote the direction. So we have three of them. Unit vector I, for instance, unit vector I is going to be equal to the component x over the magnitude, and it's going to be equal to the cosine of the direction angle. And we have the other two, we call them j and k, and they are running at y and x and z, respectively. And of course they are calculated with the component over the magnitude, which means that they are equal to the cosine of the direction angle. So for instance, if we previously stated that a vector A is going to be equal to 4, minus 3, 5, now we're going to express it at 4 in the direction of I, minus 3 in the direction of j, plus 5 in the direction of k, and it's kind of the same as stating some kind of equation where you have x, y, and z, right? This is easier because whenever you want to add vectors or subtract vectors, what you do is you add i's with i's, j's with j's, k's with k's. So previously in elementary school they stated that 5x minus 4y plus 3z, and then you're going to add to, for instance, 3x minus 3y minus 2z, and then you just add 5x with x, for instance, 8x, and y's with y's, for instance, 7y, and then, for instance, plus 1z. Well, it's going to be exactly the same now with the notation of these vectors. Then what you're going to do, instead of x, y, and z, you're going to state I, j's, k's, and you're going to be adding i's with i's, j's with j's, k's with k's. So now this is the vector. So let's just remember, we saw three concepts here. The first concept was the difference between scalars versus vectors. The second concept we were working with was, for instance, the direction angles and direction cosines, the magnitude, and how to decompose this three-dimensional vector. And last but not least is the concept of unit vectors that we're going to be using this notation, and of course how to add and subtract using this concept.